Welcome. We are now trying to evaluate the heat transfer coefficient and pressure drop in tubular heat exchanger. Let us quickly look into the configuration or what we have learned in the previous classes. So, we were basically trying to find out the heat transfer coefficient on the cell side, because already we have talked about the tube side heat transfer coefficient, that is for the internal flow, and now we are trying to look for the external heat transfer coefficient or the fluid flow when the fluid flow is taking over the tube, and we now want to find out the heat transfer coefficient for that configuration. So, this is particularly valid or relevant for the fluid flow over the tubes in the cell side. So, there we have tried to find out the if you remember, in case of internal flow, we have defined the Reynolds number by G d h by mu, where d h is the hydraulic diameter and G was the mass velocity given by the mass flow rate per unit free flow area, and that is how the Reynolds number was defined for the flow when the flow is taking place through the tube, inside the tube, or we call it internal flow. Whereas, if you remember that while talking about the external flow or flow over bank of tubes, we were looking for the maximum velocity where it is occurring at the minimum frontal area or free flow area, and now we can understand that this has been done because we wanted to calculate the Reynolds number based on that maximum velocity, and we are defining the Reynolds number by rho V x d h by mu, where d h is the external diameter of that tube and rho is the density, mu is the viscosity of that liquid. So, this is how we have defined the Reynolds number. So, that justifies our estimation of looking for the maximum velocity in case of that bundle of flow over bank of tubes. So, now we will just quickly recapitulate some of the things that we have learned in the earlier class. For the internal flow, we have, if it is a laminar flow, we have this kind of friction factor, and those friction factor will come in this relation for the pressure drop. And in case of in case of laminar flow, laminar internal flow, we have the Nusselt number related to the Grudge number, and Grudge number is given by this relation. This is where the flow is laminar and also it is internal flow. That means, the flow is taking place through the tube, inside the tube. Now, if we go to the next slide, this is also we have learned that in case of turbulent flow, we find that the friction factor is given by this relation, and this is valid for this Reynolds number. We have also learned that for R e greater than 2 into 10 to the power 4, the friction factor varies like this. We have also told that the Coleman J factor, which is nothing but the Stanton number into Prandtl number to the power 2/3 is equals to this relation, and this is valid for the turbulent flow, turbulent internal flow through a circular tube. So, now we will quickly go to the other two configurations that we have talked about while talking about the external flow. Now, we are talking about external flow, and this is the inline arrangement of the tubes, where V is the velocity and we have estimated this V max to be the frontal area divided by the A mean, that is equals to this is the minimum area A 1, and finally, it will be given by S t by S t minus d into velocity. So, this is for the inline arrangement of the tube. Now, if we look into the other arrangement that is possible, I mean that is in the staggered condition, we have seen that the tubes are in this staggered condition, and if we connect the center between this, they will form a kind of triangle. So, this is what is the staggered condition, where we have seen that this may the minima or the maximum velocity, it may occur at this location, or it may occur at this location. This is called A 2. So, we have also learned if the minima is occurring or the area is minimum at this point or the maximum velocity is occurring at this point, we have the maximum velocity is related to the free stream velocity by this relation, and if the minimum is occurring at this point or the maximum velocity is occurring at this point A 2, we find that the V max is related to the free stream velocity by this relation. And one of the criteria for occurring this V max at A 2, we have estimated it to be 2 S d minus d less than S t minus d, where S t can be related by ordinary Cartesian geometry. You will be able to relate the S t S d, this is the diagonal pitch, and it can be related to the longitudinal pitch and the transverse pitch by this relation. So, this is up to this part we have learned, and now how do we, once we have calculated the maximum velocity, we can calculate the Reynolds number, and once we know the Reynolds number, we would be able to find out the heat transfer coefficient. There, in generally this has been taken from the Barron's cryogenic heat transfer book. The Coleman J factor, there it has been related to, or it is related to this relation, some constant and R e to the power minus n, where this constant C and n will vary as a function of S L by d 0 and S t by d 0, where S t is the transverse pitch, d 0 is the outside diameter of the tube, and S L is the longitudinal pitch and d 0 is the outside diameter. So, these ratios are given on this side, and this is where S t by d 0 is varying on this side. So, we have C and n for each configuration. This is valid for number of rows more than 10. That means, when the flow is taking place like this, we have n number of n equals to 1, n equals to 2. So, like this we have number of rows and along the direction of the flow, and it has to be more than 10, at least 10 or more than 10. So, what happens if the number of tubes are less than 10? Then obviously, there would be some kind of correction factor that we have to take into account. So, we will come to that part later, but as you can understand that these are some discrete numbers that, I mean, it is not necessarily that the S L by d 0 will come as 1.125 or S t by d 0 will come as 1.25 or 1.5. So, we may finally, depending on the situation or the problem, we may find that we may have to interpolate some of the numbers. So, we will now go to, this is of course given for the, if you look at, this is given for the inline tube arrangement, or this is where the tubes are just one after the other. Okay. Now, what is about the staggered condition? We will find that for the staggered condition, now we have the heat transfer coefficients or correlations given for the staggered condition. Here also it is the same. I mean, it has been given in the form of as a function of S t by d 0 and S L by d 0. So, here we have some numbers and here we have similar numbers for S t by d 0. This is the Coleman J factor related to the Reynolds number. This Reynolds number is based on R d d max, where this R d d max we have already learned that R d d max is related to the maximum velocity, and we have learned how to, this is rho v max into d or the external diameter or d 0 divided by mu, and we have already learned how to calculate the V max. So, this is the correlation given for the tube banks where the tubes are arranged in the staggered condition. So, now we will look into, as we are talking, that this is something like some discrete position that S L by d 0, say for example, is this number is 0.6 and 0.9. Now, if by chance if something is coming at 0.85, or say it is not defined here, say let us look into this position, say between 1.25 and 1.5, if someone is finding that his number is 1.4, he may find it difficult to find out exactly what would be the number for the C and N. So, as an alternative, we have another set of correlations given in this heat exchanger selection, rating and thermal design part by Kakak et al. We find that here this is defined in as a function of, say, as a rather as a function of Reynolds number range, different range of Reynolds number, and there are different correlations for the inline tube arrangements. So, depending on the Reynolds number or Re max, we will be able to find out what are the heat transfer appropriate Nusselt number. This is related to, this correlation is again given by in terms of the Nusselt number. The earlier correlation was in terms of the Stanton, the Coleman J factor. Now, here also we will find that this correlation is valid only when the number of rows are more than, or at least number of rows are 10 or more. So, we have to apply that correction when the number of tubes or layers are rows are less than 10. So, we will come to that part later. So, now let us look into the configuration where the tubes are arranged in staggered condition. So, similarly, we have the heat transfer coefficients or correlations given for the, it is. So, these are the correlations for the staggered arrangement. When the tubes are arranged in staggered condition, these are the set of correlations. This is relating the Nusselt number, the Reynolds number and Prandtl number, and this is Prandtl number B and Prandtl number W. So, they are different. This is Prandtl number B and Prandtl number W. They are different, both are the Prandtl number, but this is evaluated at a bulk mean temperature, this is evaluated at the world temperature. So, that is the difference we have in these two numbers, and this REB also again this is evaluated at the bulk mean temperature. So, you will also find another term here, that is Cn. Here also we find a number Cn, and in the earlier correlation also you will find that we have there is a term Cn, and that Cn takes care of the number of layers. If it is less than 10, it will be some factor, but if it is more than 10 or equal to 10, then it becomes 1. So, that is how the correction factor for number of rows less than 10 is taken into account automatically in this correlations. So, now if we have the correlations available for the tube side, the cell side, where the tubes are arranged in either in inline configuration or they are arranged in staggered condition. So, based on this information, as we have said earlier, that we have to now take account of this Cn. How to estimate this Cn? We will now find that there is a graph where we can correlate this Cn. This is Cn as a function of number of tubes. So, we see that if the number of tubes are 1, then we have certain kind of Cn value for different Re values also. If the Re value is between 10 to the power 3 and 10 to the power 2, we have certain kind of correlation. If Re is greater than 10 to the power 3 or 1000, then we have some other kind of relation. Please note that this dotted line is for the staggered condition and the continuous line is for the inline condition. So, if we have the tubes arranged in inline condition, then we should look for this curve. If they are in the staggered condition, depending on the Reynolds number, we either we look for this curve or we look for this curve. If the Reynolds number is more than 10 to the power 3, we find that this relation, what I mean is this graph will tell you what would be the correction factor corresponding to number of rows equals to 2, 4, 6, 8, 10, and if it is more than 10, you can see it is almost reaching to 1 value. So, if it is say 14 number of rows, it is almost 1. If it is say about 13, it is 0.99, it is about this point, and so on. So, or it is not only giving it's for 2, 4, 6, 8, the intermediate value can also be taken as 3, 5, also we can evaluate it at these numbers 9, etc. So, depending on the number of tubes, if it is less than 10 or 12, then we can accordingly take care of that correction factor that we have to incorporate within that correlation that has been given in the earlier slides. So, now we will try to quickly look into a small problem that we can try to solve. Here it is saying that atmospheric air is flowing across a bank of staggered tubes and the number of tubes are 8. So, they are arranged in 8 rows along the flow direction. The diameter of the tube is given, the longitudinal spacing and the transverse spacing is also given. The upstream velocity is specified and it is flowing at a condition of 20 degree centigrade. So, if the surface temperature of the tube is maintained at 180 degree C, then we are supposed to find out the average heat transfer coefficient. So, let us try to solve this problem. So, what are the things that has been given to us? We already know that we have some number of tubes. How many number of layers are there? Like this we have 1, 2, 3, 4, 5, 6 and we have to add 2 more. So, like this we have 8 number of rows. So, 1, 2, 3, 4, 5, 6, 7 and 8 and the flow direction is this. This velocity v is 6 meter per second. The diameter of the tube is already specified, its diameter is 1 centimeter and the longitudinal spacing, that means the center to center, this distance is how much? 1.5 centimeter. We have the transverse spacing, that is this to this is 2.54. It is not to the scale and it is looking, the smaller dimension is looking more than this one, but if it is properly drawn, you will find that this is widely spaced. Okay. And what is given is that this fluid is flowing at a temperature T infinity is equals to 20 degree centigrade and the surface of these tubes are maintained at a temperature of 180 degree centigrade. So, what we now try to find out is an average heat transfer coefficient for this configuration. So, basically if you look into this configuration, you may find that in a shell and tube heat exchanger, we may have this kind of arrangement of the tubes and over which the fluid flow is taking place, and we are interested to find out the heat transfer coefficient for this configuration. So, for such configuration, often we specify or we supply you the heat transfer coefficient, but in reality we may have to calculate it, and we now try how to calculate this kind of heat transfer coefficient. So, now what is the starting point? We have already been given that SL longitudinal pitch is 1.5 centimeter, ST is 2.54 centimeter and diameter is equals to 1 centimeter. And first of all, we have to find out the fluid properties. We evaluate the fluid properties at 20 degree centigrade and the density is 2045 kg per meter cube. Then we have the Cp, this is equals to 1.005 kilojoule per kg Kelvin. Then we have the viscosity 1.82 into 10 to the power minus 5 Newton second per meter square. Then we have the Prandtl number equals to 0.713 and the thermal conductivity is equals to 0.0257 watt per meter Kelvin. And also this is Prandtl number B and evaluated at the bulk mean temperature, and PRW, that is the world temperature, that is 180 degree centigrade, this comes out to be 0.685. So, these are the values. We know the number of rows are 8 and the velocity v is equals to 6 meter per second. So, with this information, now we try to calculate the different parameters. What are the different parameters that we have to find out? First of all, we calculate the diagonal pitch, that is equals to root over SL square plus ST by 2 whole square and then square root. So, this comes out to be 1.95 centimeter. Then we have SD minus D, that is equals to 0.95 meter. You can understand why we are trying to find out SD minus D, because we do not know exactly at what location that minimum free flow area is there, or we are rather trying to find out where the maximum velocity is occurring. So, then we will try to find out ST minus D by 2 and that comes out to be 0.77. So, now we see that SD minus D less than ST minus D by 2, that is the correlation, condition that is necessary for the velocity to be maximum at A2. But this is not getting satisfied, because 0.95, this is equals to 0.95 and this is 0.77. So, this condition is not true. So, this is not less than. So, we can understand that the minimum area is occurring at A1 and we have to evaluate the velocity V max is equals to ST by ST minus D and V. So, this will come out to be, ST was how much? ST is 2.54 and 2.54 minus 1 into 6, this will come out to be 9.9 meter per second. So, once we know the velocity maximum velocity, then we can calculate the RE max, and that will be V max rho into V max into D divided by mu, and this becomes 9.9 multiplied by 0.01 meter is the diameter and 1.2045 is the density of the air divided by the viscosity 1.82 into 10 to the power minus 5. So, this gives you the Reynolds number 6549. So, once we have decided the Reynolds number, we can look for the appropriate correlation. If you go back, you will find the appropriate correlation for this condition, and you will find that the Nusselt number equals to 0.35 into 0.98. 0.98 is coming for Cn, because we have n equals to 8 and corresponding to n equals to 8, we have to look into that chart and there we will have the correction factor 0.98. Then we have R e to the power 0.6. This is corresponding to an R e equals to 6549. So, there we will find that the R e variation is R e to the power 0.6. Then we have P r evaluated at the bulk mean temperature, that will come at P r b to the power 0.36, and then P r b by P r w, that comes out to be 0.25, and then you have S d by S longitudinal as 0.2. So, this when we evaluate, it comes out to be 66.3. So, once we know the Nusselt number, this can be related to H d by k, and we have the value of k, we have the value of d. We can find out the heat transfer coefficient, that will come out as 170.4 watt per meter square Kelvin. So, in general, that value which we otherwise supply in different heat transfer calculations, now you have learned how to calculate it from different correlations, and with that expression of the heat transfer coefficient, we would now be able to find out different other parameters which are necessary. Thank you for your attention.